Let's review the limit laws for quotients. So the goal here is to understand this limiting value of the quotient of two functions. And right off the bat, we'll make the comment that this summary that we're about to reproduce applies, it's equally valid when a is a real number, or if you're taking the limit as a goes to infinity or a goes to negative infinity. In all three of these cases, the following rules still apply. And we're going to break up our analysis into 9 cases. The numerator, f, the limiting value could be 0 or a non-zero constant, or that limit could diverge to either positive or negative infinity. And similarly for the denominator. Although we have to make one small but important caveat. We don't want g of x to actually be 0 near a. In other words, we want to exclude a kind of pathological case where the graph winds up crossing the x-axis infinitely many times as you approach a. That's going to produce quite spectacularly wild behavior in the quotient. So we want to get rid of that case. Now the good news is, as a practical matter, most of the functions you will meet do behave this way. So they'll approach 0 through non-zero values close enough to a to avoid this pathology in the analysis. So with that caveat in mind, let's keep going. The easiest cell on this board is the middle cell. That's where the limiting value of the numerator and the denominator are both non-zero. It's pretty intuitive that the limit of the quotient should be the quotient of the limits. Similarly, if the numerator is going to 0 and you're dividing by something that's approaching some non-zero constant, that quotient should have a limit of 0. And similarly, if the numerator is exploding on you, its magnitude is getting larger, that is, it's either diverging to infinity or negative infinity, dividing through by essentially a constant, which is what's happening for g near a, that's not going to change the result, really. So you're either going to get plus or minus infinity, and the sign depends on the signs of the functions themselves, which you have to work out on a case-by-case basis. So where do we go next? This cell is by far the most interesting cell. This is sort of every derivative you take is a 0 over 0 form, really, when you take the limit of secant slopes. These are the forms that are completely unknowable until you do further work. You usually have to apply some sort of algebra, or if you have some ad hoc trick you can use in particular cases, you can do that. Or now you might use L'Hopital's rules, a way of attacking 0 over 0 forms. So the point is, intrinsically, you don't know what the limiting behavior is. You have to do more work to figure it out, and that's what we mean by an indeterminate form. Closely related to the 0 over 0 form is the infinity over infinity form. In fact, you should convince yourself that every 0 over 0 form can simply be rewritten by taking the reciprocal of the reciprocal. You can always rewrite a 0 over 0 form as an infinity over infinity form, and vice versa. So these are really two faces of the same coin. Now, in this cell, the numerator is going to 0, the denominator's diverging to infinity or negative infinity. That's only going to make the magnitude even closer to 0 when you take the quotient. That limiting value, not surprisingly, is 0. And similarly, if your numerator is going to a non-zero constant, that's not going to help the situation. You're still going to divide by something that's blowing up in magnitude, and so that limiting value should be 0. Up here, if your numerator is going to a non-zero constant, but your denominator is actually going to 0, so for example, you're dividing by 0.0001 and then 0.000001, well, you're dividing by 10 to the negative 3 or 10 to the negative 6. That's like multiplying by 10 to the third, 10 to the sixth. The upshot is you're basically making the magnitude even bigger, and it goes to infinity. And similarly, if you've already got a numerator that's going to infinity or negative infinity, and you divide by something close to 0, you're just making it go to infinity faster. So take a look at this table. You'll notice a certain symmetry. There's a diagonal line going from the upper left to the lower right, and reciprocating the original function f and g flips the roles of those two functions, and the whole table flips across that line. And if you like, the reciprocal of 0 is infinity, and the reciprocal of infinity is 0. That's what flips the table. And then k over L would turn into L over k. So there's an interesting symmetry there that sort of unites the whole thing. But you should be comfortable with each of these 9 cells. Anytime you see one of these forms, you should understand almost immediately that you get the result that's summarized in this table. In the case of an indeterminate form, you need further work to figure out what's going on.